Hi, I'm Professor Goins. In this video, I'm going to introduce the geometric idea behind a line integral. In a follow-up video, part 2, we will look at computations of how we compute line integrals. Here I want to show you where basically the definition comes from, constructing it from the curve, the surface, that kind of a thing. All right, so here's the basic setup. I have this surface in 3 space. I have a curve in the XY plane, and what I'm going to do is think about what would the region be above the curve and below the surface. So if I took this surface and I put it on top of the curve, we would have this sort of concept of like a curved fence, right? So it could be an area, but the base of the area is curved. We want to come up with an integral that would, say, compute this area of this curved fence. So what I'm going to do is I'm going to construct an integral where the integrand, just like in Calc 1, when we compute the area under a curve, the integrand is the graph of the function. So the integrand is going to be represented by the top of the fence. The region of integration is going to be this blue curve here. So the region of integration is going to be the curve C. And the differential is going to be an infinitely short line segment along the curve C. So this is actually going to be a very small arc length. Not a straight line segment, but it's going to be a very small arc length. All right, so how are we going to construct an integral that incorporates those 3 things? Well, what I'm going to do is I'm going to start by looking at the curve C. And the curve C is going to be parameterized by this vector function, x of t comma y of t, where t ranges from a to b. And I'm going to have some sketches on this diagram, so I don't want to draw on it. But let's say this right here is my vector r of a. That means that this would start at the origin and the terminal point would land at this point right here, assuming this is my starting point, and then it would trace along this curve to where this terminal point will correspond to t equal to b. Again, that's assuming that the initial point is here. Okay, so what I'm going to do is let's see if we can construct the differential of this curve. So the way I'm going to do that is I'm going to draw a vector r of t for an arbitrary point on the between a and b. So let's just call this r of t. Okay, and the curve is going to continue tracing it out. So let's say I have another vector that I'm going to put just for a slightly larger value of t. Let's say that vector would go here. And this is going to be the vector r of t plus delta t, where delta t is positive in this case. And then the change in the arc length is going to be approximately this distance right here. Okay. Which is given by the difference of those 2 vectors. And we can label that again as the vector delta s. Or let's just say it this way. Delta s is, I guess I won't use it as a vector. I'll say it's approximately that length. So let's just say that line segment is approximately delta s. You can see that straight line segment is approximately the length of the curve. All right, so let's work with that. I have the change in arc length, or the arc length there, is approximately equal to, let's make that an approximate, the magnitude of the difference of the vectors, so it'd be the length of this vector here, r of t plus delta t minus r of t. And what I can do with that is the following. I'm going to multiply this by delta t over delta t. Now, delta t is positive, right? I mentioned that over here. Therefore, I can take it inside the absolute value, and this would be given by the absolute value of r of t plus delta t minus r of t all over delta t times the change in t. So again, let's summarize that over here. Delta S is approximately equal to that. So the change in the arc length, the length, that arc length there is approximately given by this expression. And to make that precise, what I'll do is I'll take the limit as delta t goes to 0. So if we take the limit as delta t goes to 0, I'll just abbreviate that by that red arrow. So what happens after I take the limit as delta t goes to 0 is the differential, or delta s, is going to turn into a differential ds. If you look inside the absolute value bars here, this is the derivative of r, so this would be the magnitude of the derivative of r. And then delta t is dt. So a differential arc length is given by the magnitude of the derivative of the parameterization times the differential of t, which is the parameter that we use in our parameterization. Okay? So that's what I'm going to use for my differential. Now, how do I incorporate the region of integration and the integrand being the top of the fence? Okay, so let me clean this side up and show you how to do that. All right, so let's say this was the top of the fence of that region that I drew here a little bit ago. This is the curve C down in the XY plane. So consider the following. If I pick a point on this curve, that would be given by x of t comma y of t. So that would be in the XY plane. An arbitrary point would be given by x of t, y of t. Please make sure that's on screen there. Go too far over. I'm just going to check and see if that's on screen. Looks like it might be okay. All right, so then if I look directly above that, that would be this point right here on the graph. And the way we find that is, remember that this was the graph of z equals f of x, y. So this would be f of x of t, y of t. So we can see that for our parameterization, anywhere along the curve, we have x of t, y of t. To find my point on the graph, I simply take those coordinates and plug them into the function. So in my integrand, I'll use the function f, and in the components for the variables, I will use the components for the parameterization. Okay. And then the last thing I need to do is incorporate the region of integration, being C. So before I erase this, notice that the parameterization has the parameter t. T ranges from a to b. So my limits of integration will simply be from a to b. So let me clean up the middle here and let's put it all together. Okay. So the line integral is the integral over the curve C of the function f of xy ds. So there's the notation for the line integral and the way that we evaluate it using everything that we just described. And to incorporate the curve C, we go from A to B, right? This is t equal to A, this would be t equal to B, so my limits of integration go from A to B. My function f of xy, I need to get that in terms of the parameter t. Just like since this goes from t equal to A, t equal to B, I need to get my integrand in terms of t, which means I take my original function and I plug in the corresponding components for the parameterization, meaning f of xt yt. And then I need to get my differential in terms of the parameter t, and that's what we did over here. We turned the arc length differential to a differential in terms of the parameter, so I'm going to replace ds with this expression right here in red. A little bit more space. So this would be the magnitude of the derivative of the parameterization times the differential of the parameter. Okay, so this is how we construct what's called a line integral. This is how we put it all together. In the follow-up video to this, we will show you how to compute line integrals and for various functions and for various curves.